Hello friends, today we are going to solve the questions from modern physics. These questions are from the year 2011. So total there are 3 questions. From year 2012 there is one question, and this question is from the advanced, and from 2013 we are going to solve total 6 questions. Out of these 6 questions, 5 are from advanced and 1 is from mains. So in total we are going to solve 10 questions. So first question, it was asked in the 2011, and it states that the wavelength of the first spectral line in the Balmer series of hydrogen atom is 6561 angstrom. The wavelength of the second spectral lines in the Balmer series of singly ionized helium atom is. So here we have to find out single ionized helium atom, which will be nothing but our He1 positive. And for that we are going to use Rydberg formula. And which is our 1 upon lambda is equal to r z square 1 upon n1 square minus 1 upon n2 square. And we are given Balmer series, so from based on this we can define n1 and n2. We can say for Balmer series, our n1 will be equal to 2, and for the second spectral line we can say our n2 will be equal to 4, and for second line our value of n2 will be equal to 4, and value of z for He positive for helium 1 positive, the atomic number that is value of z will be equal to 2. So we can just substitute all the values, and we get this as 1 upon lambda is equal to we have our r, z is our 2, and we have this as 2 square minus 1 upon 4 square will be equal to, this comes as 4r multiplied by 16 will be LCM, and this will be coming as 4 minus 1, that is equal to 3, and 16 goes by 4, so from here we get this as 3 by 4 times r. Therefore wavelength lambda will be equal to 4 upon 3r. We substitute value of r, we get this as 3 into 1.1 10 raised to power 7, and this will be approximately equal to 1215 angstrom. So the answer is 1215 angstrom. Next question. It was also asked in the year 2011, and it states that a silver sphere of radius 1 centimeter and work function 4.7 electron volt is suspended from an insulating thread in free space. It is under continuous illumination of 200 nanometer wavelength light. As photoelectrons are emitted, the sphere gets charged and acquires a potential. The maximum number of photoelectrons emitted from the sphere is A into 10 raised to power Z, where A lies between 1 and 10. The value of Z is. So in this case, we are given a silver sphere of radius 1 centimeter, and its work function is 4.7, and wavelength, that is lambda, is 200 nanometer. We have to find out the maximum number of photoelectrons. So first of all, we are going to find out the energy of the incident photons. Energy of incident photons, if that is given as E, will be equal to hc upon lambda, and we can substitute our hc in terms of electron volt. So this gives us our energy is equal to, we have 1242, and lambda is our 200 nanometer. This will be equal to 6.21 electron volt. And based on this, we are going to find out the maximum kinetic energy of the emitted photoelectrons. Okay. And this is initial, okay, because due to loss of the electron, it is going to becomes more and more negative charge. So obviously its electric potential is going to increase, and eventually after some time the photo emission is going to stop. We can find out that value also. So we start with our maximum kinetic energy. Maximum kinetic energy of emitted photoelectrons, and this is initial. And for that, we can say the kinetic energy maximum will be equal to energy of the photon, that is our E, minus the work function phi, and this comes as 6.2 minus 4.7. This gives us 1.51 electron volt. Now as the light will be more and more incident, the electrons, photoelectrons, will be leaving the sphere, giving the sphere the negative charge. Therefore we can say that as the sphere becomes negatively charged due to photoelectron leaving its electric potential increases. Electric potential increases. And eventually stops. Further photo emission. And this happens when the product of our charge with the potential becomes just equal to the maximum kinetic energy, which is our 1.15 electron volt. Therefore, we can say our potential V will be equal to 1.51 volts. Now we can use the standard formula for the potential of a conducting sphere, charged conducting sphere. You can say potential of a charged conducting sphere, and that formula is given as V is equal to 1 upon 4 pi epsilon naught Q upon radius r. From here we can say the value of charge Q will be equal to 4 pi epsilon naught r times potential V. And we know all these values, so we can say our charge Q will be equal to 4 pi epsilon naught is our 8.8 into 10 to the power minus 12, and radius is given to us as 0.01 multiplied by 1.51. This comes approximately as 1.68 into 10 to the power minus 12 coulombs. Now we can easily find out our number of photoelectrons. Number of photoelectrons, suppose given as n, then this n will be equal to total charge and charge on one electron. Total charge is our 1.68 into 10 to the power minus 12, 1.69 into 10 to the power minus 19. So from here we get that our value of n is approximately equal to 1.07 into 10 to the power 7. And but we are given that value of n is equal to a into 10 to the power z, and it is also mentioned that our a is greater than 1 but less than 10. So if you make 1:1 comparison, we can write that value of A is equal to 1.05 and value of Z is equal to 7. So value of Z is equal to 7. Next question. It states that it was asked in the year 2011 and states that the activity of a freshly prepared radioactive sample is 10 to the power 10 disintegration per second, whose mean life is 10 to the power minus 9 second. The mass of an atom of this radioisotope is 10 to the power minus 25 kg. The mass in milligram of the radioactive sample is. So in this case we are given disintegration, that is our 10 to the power 10. So we start with the standard formula. After time t, that is our n of t, will be equal to the initial sample n naught e raised to power minus lambda t. From here we can find out a disintegration per second. So we differentiate it, we get this as dn upon dt will be equal to, and one second, yeah, n naught lambda e raised to power minus lambda t. And so we can write dn upon dt is our 10 raised to power 10. Therefore you can write this as 10 raised to power 10 is equal to n naught lambda e raised to power, and we have this as minus 10 raised to power minus 9 times t. And at time t is equal to 0, we get that our this comes as e raised to power is 1, and so from here you can say 10 raised to power 10 is equal to n naught 10 raised to power minus 9, and we are given that the value of so from here we get our n naught. So from here we get our n naught will be equal to 10 raised to power, this comes as 19. and we can write that mass of the sample will be equal to and n naught times 10 to the power minus 25. We substitute value of n naught, that is 10 to the power 19 into 10 to the power minus 25. This gives us 10 to the power minus 6, and we need to it in the milligram. Okay, so this is our multiply by 10 to the power 3. So this gives us 10 to the power minus 3, or we can say 1 milligram. So we have this as 1 milligram. Next question. It was asked in the 2012 advance, and it states that it is basic passage type question, and it states that the beta decay process discovered around 1900 is basically the decay of neutron N. In the laboratory, a proton P and electron E minus are observed as a decay product of the neutron. Therefore, considering the decay of a neutron as a two-body decay process, it was predicted theoretically that the kinetic energy of the electron should be a constant. But experimentally, it was observed that the electron's kinetic energy has a continuous spectrum. Considering a three-body decay process, that is, N gives us a proton, electron, and a antineutrino around 1930, Pauli explained the observed electron energy spectrum. Assuming the antineutrino to be massless and possessing negligible energy, the neutron to be at rest, momentum and energy conservation principles are applied. From this calculation, the maximum kinetic energy of the electron is 0.8 into 10 to the power 6 electron volt. The kinetic energy carried by a proton is only the recoil energy. So based on this, we are given two questions. In part A, if the antineutrino had a mass of 3 into 3 electron volt per c square, where c is the speed of the light, instead of zero mass, what should be the range of the kinetic energy of the electron? And part B, what is the maximum energy of the antineutrino? Okay. So first case, it says that antineutrino has a mass. So we have to find out the range of the kinetic energy. So we start with part A. And we know that for a Q value can be calculated as kinetic energy of proton, kinetic energy of beta negative, as well as our kinetic energy of the electron. And initially, it is given that our kinetic energy of is minimum. Okay, so we start from the formula. Basic, we can say, we can write the Q value is, it is given as kinetic energy of proton plus kinetic energy of beta negative plus kinetic energy of our electron, sorry, antineutrino, my mistake. And the kinetic energy, but kinetic energy of beta negative, if it is to be taken as minimum, is our 0. Therefore, we can write that our range, therefore the value of kinetic energy of our beta negative will be greater than 0 and it will less than our Q minus, we have this is kinetic energy of our beta negative plus kinetic energy of our antineutrino. Okay. Therefore, from here we can say that our kinetic energy of our beta negative maximum will be nothing but is equal to Q. So we can say it is going to lie between the range of our, the minimum value is our 0. So we can say the range of kinetic energy of the electron lies between 0 and kinetic energy of our electron. Therefore, we can say kinetic energy will be less than equal to 0, but less than value is given to us as 0.8 into 10 to the power 6. 0.8 into 10 to the power 6 electron volt. So therefore the option A is correct. Sorry, not option A, but option D is correct. Option D is correct. And in part B, it states that the maximum energy of the antineutrino is, and we are given a two-step process also. So we can say part B, which gives us that the neutron is our proton plus electron plus our antineutrino. And we know that the Q value of the reaction is our kinetic energy of our beta negative, and for that maximum value, which we already found out, is 0.8 into 10 to the power 6 electron volt. Therefore, we can write the equation that our kinetic energy of our proton plus kinetic energy of our beta negative plus kinetic energy of our antineutrino is equal to Q. But it is mentioned that this kinetic energy of the proton is approximately equal to 0. Therefore, we can say that our kinetic energy of our antineutrino will be equal to our value of Q under the condition that our kinetic energy of this beta negative is equal to 0. And therefore, we can say that our maximum energy of antineutrino is equal to the maximum kinetic energy of the electron is equal to maximum kinetic energy of electron. And this maximum kinetic energy of electron, it is already given to us as 0.8 into 10 to the power 6 electron volt. So nearly we can say option C is correct. Next question, it was asked in the 2013 advance, and it states that a freshly prepared sample of a radioisotope of half-life 1386 second has the activity of 10 to the power 3 disintegrations per second. Given that log of 2 is 0.69, the fraction of the initial number of nuclei expressed in nearest integer percentage that will decay in the first 80 seconds after the preparation of the sample is. So we are given the half-life of the sample is given. So you can say the half-life, that is our T half, is 1386 seconds, and the time elapsed is our 80 seconds. So you can say value of T is our 80 second, and we have to find out the fraction of the decay. So that we can use the formula that the fractional decayed is equal to 1 minus e raised to power minus lambda t, and we can easily find out our lambda. Lambda is equal to natural log of 2 T half, which gives us 0.693 and divided by 1386, and this gives us that it's approximately equal to 5 into 10 to the power minus 4 per second. So therefore we can say that our fractional decay after time t is equal to 80 seconds fractional decay after t is equal to 80 seconds. Same formula, but we are going to put the values, and this gives us 1 minus e raised power, and we have this as minus 5 into 10 to the power minus 4 and multiply by 80, and this approximately equal to 0.0392, and it has to be converted in the percentage. So multiply by 100, so approximately it equal to 3.92%, and nearest integer we can write that this is approximately equal to 4%. Next question. It was asked in the 2013 advance. It is a passage based question, and it states that the mass of nucleus X is less than the sum of the masses of A minus Z number of neutrons and Z number of protons in the nucleus. The energy equivalent to the corresponding mass difference is known as binding energy of the nucleus. The heavy nucleus of mass m can break into two light nucleus of masses m1 and m2 only if m1 plus m2 is less than m. Capital M. Also, two light nuclei of masses m2 and m3 can undergo complete fusion and form a heavy nucleus of m prime only if m1 plus m4 is greater than m prime. The masses of some neutral atoms are given in the table below. So based on this, we are two questions. In part A, the correct statement is asked, and in part B, it states that the kinetic energy of the alpha particle when the nucleus of polonium at rest undergoes alpha decay. So we are given part A, and part A is having, let me write it 1 and 2. So this is our 1 and this is our second. So first of all, let us solve part 1. In part 1, we are going to take the options one by one and try to find out the energetic relationship between the left side as well as the right side. Okay. So in the part 1, option A, it states that nucleus lithium can emit an alpha particle. Okay. So we can write the reaction based on this. It states that our lithium, which is our 6 and 3, it emits alpha particle. So this will be giving us a hydrogen 1 and 2 plus our helium, that is 2 and 4. So this particular we are going to check whether energy satisfies this particular relationship or not. So we can say check if this is energetically allowed or not. For that, we are going to use the respective masses because it is given. So we can say masses. First is for our left hand side, and left hand side we have a mass of our lithium 36, it is given as 6.0513, 6.01513 AMU. And on our, let us call this is our left hand side, and similarly on the right hand side we have a mass of our hydrogen plus mass of our helium, and these values are given to us. So this is 2.014102 plus 2.4102 plus that of helium is 4.002603, and this comes as 6.016705 AMU, and let us call this as our RHS. So from here we can clearly see that our RHS is greater than our LHS. Therefore, decay is not possible. Decay is not possible. So option A is incorrect. We are going to check all these options. And we have our option B. And option B states that nucleus polonium can emit a proton. And this because polonium is very heavy nuclei. So here the alpha emission will be favored as compared to proton, because the proton is going to require a certain amount of high energy overcoming the nuclear potential. Okay. So we can say polonium can emit a proton. Can emit a proton, and we can say that this is not favored as it would require overcoming the nuclear potential. The nuclear potential, and is rare. Therefore, option B is also incorrect. We come to the option C. And option C states that deuteron and alpha particle can undergo fusion. Okay, so basically they can combine producing a lithium. So we can write that our deuterino plus helium. Okay, sorry, I previously called this as hydrogen. This is not hydrogen, this is deuterino basically. So H12 is our deuterino, and plus the helium to 4 it fuses and produces our lithium, that is our 6 and 3. Similarly, we are going to find whether energetically this reaction is possible or not. So let's find out the mass on the left side. So our left hand side will be giving us a 2.014102 plus 4.002603, and their summation will be our 6.016705. And from the right side we have only one possibility, so we get our RHS is equal to 6.01513. So if we make a comparison, we can clearly see that our left hand side is greater than right hand side. Left hand side is greater than our right hand side, or basically we can say that excess mass converts to energy. Excess mass converts to energy, which basically means that fusion is allowed. Fusion is allowed, therefore the option C is correct. And finally, the nuclei zinc and selenium can undergo complete fusion. Same, we can check it. That is our option D. And it says that our zinc, that is 3079 plus selenium, and this will be 3482, and it will be giving us a product that will be our GD 151. And this comes as 64. Similarly, their mass, that is the left hand side, will be equal to, we have this as 69.925325 plus 81.916709, and this total comes as 151.842034. And our right hand side single product, which is our 151.919803. Okay, and in this case, especially in fusion, condition is also given to us that, let me write it here, I should have explained it previously because first case was also fusion, C part, but anyways, so in the fusion it states that our M3 plus M4 can fuse if it is less than of M prime. This is the condition for the fusion. So this is our M prime, and this is the summation of our M2 plus M3. So from here we can clearly see that our M2 plus M3 is less than our M prime. Therefore, not M2 but M3 and M4. M3 and 4, M3, M4. And For fusion it has to be greater than. Okay, so let me correct myself here, it has to be greater than for fusion, and this is for fusion, the given condition. But in this particular case we can clearly see that our M3 plus M4 is less than our M prime, therefore fusion not allowed. Fusion not allowed. So option D is incorrect. Now we come to the part 2, in which we are supposed to find out the kinetic energy when polonium at rest goes the alpha decay. So part 2, we have our polonium, that is our 84 to 10. It is going to produce us a lead, which will be our 82 and 206. Alpha decay, that is our helium 2 and 4. So let's find out their respective masses. And mass of polonium is our 209.982848, and here we are having of our lead is our 205.974455 plus 4.00, and this is about 2603. So from here we are going to find out the mass difference. Mass difference, that is our delta M, will be equal to our initial mass minus mass of our lead plus mass of our alpha particle. We know all these values. M initial is our 209.982848 minus, and we have this as 205.974455 plus 4.002603. So we get this mass difference delta M is equal to 0.005790 AMU. From here we can just convert this mass defect into energy. So we can say our energy Q will be equal to 0.005790 multiplied by 931.5 mega electron volt. This comes as 5.395 mega electron volt, and this energy will be the total kinetic energy that will be shared between the two products. Okay, so we can say this is total kinetic energy shared between two products. We can use, and it also states that both of the products are moving, so we can use the conservation of momentum. Conservation of momentum. And from there we can write that our K alpha will be equal to total energy multiply by mass of our lead and divided by the mass of the lead as well as mass of our alpha particle. And we can just approximate it. Q we already know is our 5.395, and we can write this as 206 divided by 206 plus 4, and this comes as approximately as 5.29 mega electron volt. Therefore, we can write kinetic energy of alpha in kilo electron volt will be equal to 5290 kilo electron volt. So the closest one, because I approximated it, will be equal to our 5316 kilo electron volt. Option A is correct. Next question. It was asked in the 2013 advance, and it states that the radius of orbit of electron in a hydrogen-like atom is 4.5 times a0, where a0 is the Bohr radius. Its orbital angular momentum is 3h upon 2p. It is given that h is a Planck constant and r is a Rydberg constant. The possible wavelengths when the atom de-excites is or are. So we are given that the radius of electron orbit is given to us. So we can say radius of electron orbit is our r is equal to 4.5 times a0, and we are also given that I think this equation is wrong. It should be 3 by 2 h divided by 2 pi. I think it should be like this. Yes. So this, it should be 3 by 2 h upon pi. It should not be p, but it should be pi. And so we are given the angular momentum it is given as 3 by 2 h upon pi. And the general formula for angular momentum we also know is our nh upon 2 pi. This gives us that value of n is equal to 3. And we also know that the radius of the nth orbital, the allowable radius, so you can see the radius r of n of the nth allowed orbit is our r of n is proportional to n square upon z. And here, from here we can say our r is, if we, because a naught is our standard constant, therefore we can say that our r of n will be equal to 0.5. Zero point 4.5, sorry. Therefore, we can write that 4.5 is equal to, value of n is our 3, and from here we can easily find out value of z. So this gives us that value of z will be equal to 2. Next, what we are supposed to, wavelength. Okay, so we can now use the Rydberg formula, and we can say the wavelength one upon lambda is equal to our r z square 1 upon n1 square minus 1 upon n2 square. Now, the initial state of n is our 3. So there are, you can say, 3 different ways in which the atom can de-excite itself. So you can say the atom can de-excite itself in 3 different ways from n is equal to 3. So first is our, that value of n2 is our 3, and it de-excites for n1 is equal to 1. And based on this, we can say our 1 upon lambda 1 is equal to, we have our 2 square r 1 upon 1 minus 1 upon 9, and this comes as lambda 1 will be giving us 9 upon 32 times r. This gives us a lambda 1 is equal to, this will be our 9 upon 32 times r. And our second one will be from n2 is equal to 3 to our n2 is equal to n1 is equal to 2. So we can say 1 upon lambda 2 is equal to 2 squared times r, and we have this as 1 upon 4 minus 1 upon 9. This gives us lambda 2 is equal to 9 upon 5 times r. And finally, we have third, that is our n2 can be from 2 to n1 is equal to 1. So we have 1 upon lambda 3 is equal to 4r, and we have this as 1 upon 1 minus 1 upon 4. This gives us that our lambda 3 is equal to 1 upon 3r. So we have 9 upon 32 and 9 upon 5 and 1 upon 3. 9 upon 5 and I think this 1 upon 3 are okay. So option A and C are correct. A and C are correct. Next question. We are given, it was asked in the year 2013 advance, and it states that a proton is fired from a very far away towards the nucleus with a charge Q is equal to 120 times E, where E is the electronic charge. It makes closest approach of 10 FM to the nucleus. The De-Broglie wavelength in the units of FM of the proton at its start is various values of MP as well as 1 upon 4 pi epsilon naught as well as 1 FM in terms of meter is given to us. So here we are going to, we can say, relate our kinetic energy with our electrostatic energy and kinetic energy with the momentum, and that is going to provide us the solution. So first of all, let's calculate initial kinetic energy. Initial kinetic energy, let us suppose we call this as kinetic energy initial, and the kinetic energy initial will be equal to the electrostatic potential energy closest at the closest approach. So we can say our kinetic energy initial will be equal to electrostatic potential energy, and that is what call as UF at the closest approach. At the closest approach. And electrostatic potential energy. So from here we can write that our Ki initial is equal to potential energy at the closest approach. So we can say our kinetic energy initial is equal to 1 upon 4 pi epsilon naught, and we have charge on the nucleus multiplied by charge on proton, and the distance of closest approach is, let us suppose, given as r, and we substitute the values. This is our 9 into 10 to the power 9, and we have 120 E multiplied by E, and this is about 10 into 10 to the power minus 15. So we get our kinetic energy initial will be equal to 9 into 10 to the power 9 and 120 E square divided by 10 to the power 14. Now we can relate this kinetic energy initial to the momentum. So you can say that our kinetic energy is also given as kinetic energy initial. In terms of the momentum, it will be our p square divided by 2 mass of the proton. So we equate, we get our p square divided by 2 into mass of proton will be equal to 9 into 10 to the power 9 multiplied by 120 E square and 10 to the power minus 14. So from here we can write that our momentum, or we can say p square, will be equal to twice into mass of proton multiplied by 9 into 10 to the power 9 multiplied by 120 times E square and 10 to the power minus 14. Now we can find out our De-Broglie wavelength. De-Broglie wavelength, whichever lambda will be equal to h upon p, and we are going to square them. Lambda square is equal to h square upon p square. We substitute the values and we get this as h square multiplied by, and we have this as twice into mp multiplied by 9 into 10 to the power 9 into 120. This here comes as E square, and in the numerator it comes as 10 to the power minus 14. And let's substitute the values. This will be giving us 4.2 into 10 to the power minus 15 whole square multiplied by 10 to the power minus 14, and we have this as 2 into 5 by 3 multiplied by 10 to the power minus 27 into 9 into 10 to the power 9 into 120. Now it is part of calculation. So we can say our lambda square is approximately equal to 49 into 10 to the power minus 30, which gives us that our lambda is equal to 7 into 10 to the power minus 15, and this will be in terms of meter, or we can say 7 FM. In terms of FM is 7 FM. That is a femtometers. Next question. It was asked in the 2013 advance, and it states that the work function of silver and sodium are 4.6 into and 2.3 electron volt respectively. The ratio of slope of stopping potential versus frequency plot for silver to that of sodium is. And in terms of the, you can say, slope intercept form, we can write the equation for our stopping potential. So we can say the slope of the stopping potential which is represented as Vs versus frequency is, that is given by the equation that our stopping potential Vs will be equal to h upon E F minus work function upon E. Here h is the, you can say, Planck's constant, E is the charge on electron, and phi is a work function. And from here we can clearly see that our slope is equal to h upon E. So the slope is only dependent upon our value of h as well as E, which is basically a standard or constant values, and it is independent of work function, independent of phi. So we have to find out the ratio. Therefore we can say ratio for ratio of slope for silver to sodium, which we can write h upon E divided by h upon E. This comes as 1. So ratio is our 1. Next question. It was asked in the 2013 mains, and it states that in a hydrogen-like atom, electron make a transition from an energy level with a quantum number n to another with quantum number n minus 1. If n is very much larger than 1, the frequency of radiation emitted is proportional to. So here we have to basically find out the frequency proportional in terms of when n is greater than, larger, very much greater than 1. So we already know the basic formula, that energy of the level n that is, suppose our E of n, it is given as minus r z square upon n square, where r is a Rydberg constant and z is our atomic number, and for hydrogen-like atom value of z is equal to 1, and it makes a transition from n to n minus 1. So we can say that the energy difference or we can also say photon energy emitted. And the difference is our delta E will be equal to n and n minus 1. So this gives us minus r z square upon n square plus r z square upon n minus 1 whole square. And we are going to use binomial solution because n is very much greater than 1. Therefore, we can say we are only interested in solving this part. So n minus 1 whole square will be approximately, or we can just open the bracket first. This will be equal to n square minus 2n plus 1. This will be approximately equal to n square minus 2n. And it is in the denominator. So we can say 1 upon n minus 1 whole square will be now approximately equal to 1 upon n square minus 2n. This can be further written as, we take n square as common, so this comes as n square 1 minus 2 upon n, and approximately 1 upon n square 1 minus 2n whole raised to power minus 1, which comes as 1 upon n square 1 plus 2 upon n, and this gives us 1 upon n square plus 2 upon n cube. So we can say our delta E is equal to r z square, we can take common, and we get this as 1 upon n square minus, sorry, not minus but plus 1 upon n cube minus 1 upon n square. Yeah, and our 1 upon n square cancels out, so this comes as our r z square multiplied by 2 upon n cube. So therefore, frequency of emitted photon if represented as f, so then this f will be equal to delta E upon h and approximately 1 upon n cube, or we can write this as frequency is proportional to n raised to power minus 3. N raised to power minus 3. So this completes all the 10 questions. So in this question we did advanced part from 2012, one question, as well as advanced question from our 2013, 5 questions. Okay, total we did 10 questions. So this completes all the 10 questions. Thank you.